All right, let's talk about the general Lebesgue integral. So let's say we have a measurable e, and throughout this lecture, like always, e is measurable. Let's say we have some extended valued function on e that's measurable. And remember, we have f plus is a maximum of f of x and 0. F minus is the maximum of minus f of x and 0. Remember that f is f plus minus f minus. You can just check, plug x in and do the two cases when f of x is positive or when f of x is less than or equal to 0. And also, there's no ambiguity here. One of them is always going to be 0. Either f of x is bigger or equal to either f of x is positive or f of x is less than or equal to 0. So you're never going to have infinity minus infinity here. One of them is always 0. Okay. We've never really used this, but you can check very easily that absolute value of f of x is f plus f minus. Let's actually see why that's true. Well, we have two possibilities. If f of x is bigger than 0, then f minus is 0. Okay, so f plus f minus is f plus. Well, absolute value of f of x is f of x, okay, which is f plus of x if f of x is bigger than 0. So they both become f plus of x. On the other hand, if f of x is 0 or negative, then f plus is 0, f minus is minus f of x. Okay, so f plus f minus is minus f of x. And, well, that's exactly what absolute value of f of x is. If f of x is less than or equal to 0, it's minus f of x. So, yeah, so you easily show that this is true. And you should, I mean, if what I said was if I said that a little fast, again, just try it yourself and do those two cases that I mentioned. Okay, so by definition, if f is as above, so f is measurable, extended, real valued function, you'd say f is integrable if very simply this integral is finite. Okay. And there's no ambiguity here. We know how to integrate absolute value of f of x. It's a non-negative function, so its integral exists, period. Okay, so a very easy proposition is that f is integrable if and only if f plus and f minus are. And why is that? Well, absolute value of f of x is f plus of x plus f minus of x. So absolute value of f of x is always bigger or equal to the maximum of f plus and f minus. Okay. Or rather, absolute value of f of x is always bigger or equal to both f plus of x and f minus of x. So the integral of absolute value of f of x is bigger or equal to the maximum of these two. Okay. On the other hand, absolute value of f of x, again, is f plus of x plus f minus of x. So if this is finite, then certainly both of these are finite. And if both of these are finite, then certainly integral of absolute value of f of x is finite because, well, it's just integral of f plus integral of f minus. Okay. So yeah, really not a whole hell of a lot to this one. All right, so that leads us to the following definition. If f is integrable, then we define the integral of f of x to be the integral of f plus minus the integral of f minus. And there's no ambiguity here. F plus and f minus are two non-negative functions, we can integrate them, and both of these integrals are finite because f is integrable. So this is a real number minus a real number, and hence it's well defined. All right, so let's get this interesting proposition out of the way, which is that integrable functions are not that exotic. In fact, they are real valued almost everywhere. Okay. So why is this true? Well, we're going to use Chebyshev's inequality. So pick a natural number n. So the set of all x and e, where f of x is plus or minus infinity, one of the two, is certainly equal to the set of all x and e, where absolute value of f of x is infinity. I mean, absolute value of minus infinity we define as plus infinity, kind of an obvious thing to define it as. So in that regard, obviously this makes absolute value of f of x, non-negative, in case that wasn't clear. Well, if absolute value of f of x is infinity, infinity is certainly bigger or equal to n for every n. So this here, set of all x, where absolute value of f of x is infinity, is a subset of the set of all x and e, where absolute value of f of x is bigger or equal to n. And by Chebyshev's inequality, this is less than or equal to, this is my lambda, to 1 over n times this integral. But this integral we're assuming is finite. That's the definition of integrable. Well, it's measurable and the integral is finite. So the measure of this set here is less than or equal to 1 over n times something that is a real non-negative number, not infinity. It's a real positive number, or it could be 0. It's a real non-negative number. So you can let n go to infinity. And this forces this set to have measure 0. So the set of all x and e, where f of x is either plus or minus infinity, is 0. Okay. All right, and from now on, we're going to therefore assume that f is actually real valued if f is integrable. Very simply because if f is an extended valued function, that is, if f is an extended valued function, then we can redefine it on a set of measure 0 in any way, shape, or form we want to keep the integrals the same. And in particular, we could do something like redefine f on this set here as 0. So let's say f tilde is f of x if f of x is real, and 0 if f of x is plus or minus infinity. Then these two functions are equal almost everywhere, and therefore they have the same integral, just because we know it's true for non-negative functions, that two non-negative functions are almost everywhere equal, implies that their integral is the same, and just apply that to this definition here. That's it. And you can check that if two functions are equal almost everywhere, then so are their positive parts, and so are their negative parts. The plus being the positive part, and the minus being the negative part. Okay. So let's get to a very useful but fairly trivial result, and that is the integral comparison test. So if I have a measurable real-valued function, and there exists an integrable non-negative function g with absolute value of f less than or equal to g on e, then f is integrable. And like I said, it's absolutely trivial, but we use this fairly often because it's just so useful to to have this kind of little test here, and it's useful to not have to restate this over and over and over and over again. So, but yeah, so I mean the proof is just integrate both sides, And I have to assume G is measurable. If G is measurable, then we know, the Lebesgue integral of non-negative functions is monotone. So the integral of absolute value of f is less than or equal to the integral of G, and that's less than infinity. All right, so let's get to integrating complex valued functions. And again, this is not academic. For engineering applications, you want to define Fourier transforms, Fourier series, and so you need to integrate complex value functions. And if you actually pick up an electrical engineering book, a signal processing book, a computer engineering book, you will see it littered with complex numbers because there's no reason not to deal with complex numbers. They just make life easier. They're very useful. So anyway, so let's say we have a complex valued function on E. So let's say, this is just standard terminology. Let's say U of x is the real part of f of x, and v of x is the imaginary part of, this should be f of x. There is no g here. So sorry, this is the imaginary part of f of x. So then u and v are real valued. Okay. Right. So usually we say z is x plus iy, but that doesn't really make sense here because, x is our domain variable. So that's why for lack of anything better to use, we use u and v. In Calc 3, you've sometimes used u and v to denote a function that spits out an element in R2, or you probably did that in advanced calculus of several variables. All right, so we say f is measurable if u and v are. And again, this should be, so this should be actually the imaginary part of, sorry about that. Imaginary part of f of x. That. Okay. Right, so f is measurable by definition if u and v are measurable. And if f is measurable, then so is its modulus because, well, u is measurable, v is measurable, u squared is measurable, v squared is measurable. So square root of u squared plus v squared is measurable. So, yeah. All right, so if this is measurable, C valued, complex valued, then we say f is integrable if u and v are. And we define the integral in kind of the obvious way. It's just we integrate the real part plus I times the integral of the imaginary part. So kind of just, pretending that, or basically it has to be this, essentially. We're not pretending anything. It's got to be this. Because in some sense, the integral better be linear. So you better be able to integrate the sum as a sum of the integral, and you better be able to pull out the I. So this is a very reasonable definition of this integral. Okay, so another way of looking at this is to integrate a complex valued function and writing it as a real part of f of x plus I times the imaginary part of f of x. That's just going to be integrating the real part I times integrating the imaginary part. Okay. So we have the following useful integral comparison test. Same thing if there is a g, non-negative and measurable, where absolute value of f is less than or equal to g on e, then f is integrable. And the proof is fairly straightforward. Absolute value of u is less than or equal to u squared plus v squared square root, and that equals modulus f, and that's less than or equal to g. Do the same thing for v. So if such a g exists, then u and v are integrable, and hence, by definition, f is integrable. All right. All right, so let's get into the basic properties. I'm not going to dwell on this much. Integration is linear, monotone, and behaves like measure in this sense here. Okay, and we'll talk more about 3 in the next video, proving that actually this works for the countable union of disjoint measurable sets. So that integration really behaves like Lebesgue measure. All right, so let's prove 1. So first of all, this is integrable because of the triangle inequality that I mentioned in the last video. In particular, the triangle inequality says I can take this absolute value right here, kind of collapse it in, and it's the absolute value of alpha f of x plus absolute value of beta g of x. And I should mention alpha and beta are complex numbers. They're just complex scalars. And then we can further collapse absolute value of alpha f of x into absolute value of alpha times absolute value of f of x, and the same thing for beta g. Well, this is a real number. This is a non-negative real number. This is a non-negative real number. And so these two are certainly integrable. Or rather, this plus this is certainly integrable. I integrate this whole thing here. It's not infinity. So that means that this is integrable. Okay, so you can look at page 87 for a proof in the book where this is true. It's very easy. It's just a pain in the ass to do. When alpha, beta, f, and g are all real, how do you prove it? Well, you basically just write everything in terms of its positive part and its negative part. In do cases, alpha and beta are positive or negative. And then use the fact that integration is linear. When we're integrating we're integrating non-negative functions times positive numbers. So it's very, very easy. It's just many annoying cases. So we're going to assume this is true for real numbers. Again, it's just based on easy consequence of the fact that integration is linear when we're dealing with non-negative functions and positive scalars, positive alpha and beta. So to get an idea of how to do things with complex numbers, let's prove this now in general, where alpha and beta are complex scalars and f and g are complex values. So as usual, it's enough to show that we can integrate a sum as the sum of the integrals, and that we can pop out scalars. So popping out scalars when alpha is complex and f is complex value, that's a homework. It's pretty easy, but it's a good homework if you're not familiar with complex numbers. You just multiply out alpha as real part of alpha plus I times imaginary part of alpha, whole thing, parentheses, times f of x, which is, real part of f of x plus the I times the imaginary part of f of x, parentheses. Do the FOIL, and check that it's going to be the same thing as this. Okay, so let's prove this. So let's say f is u1 plus I v1, a little easier than real part of f of x plus I imaginary part of f of x. Let's say g is u2 plus I v2. Okay, so let's add up f plus g. F plus g is u1 plus u2, parentheses, plus I times v1 plus v2. So by definition, the integral of this complex valued function is you integrate the real part, which is u1 plus u2 times I, the integral of the imaginary part, v1 plus v2. Okay. Now I know from this here that the integral of the sum for real value functions is the sum of the integrals. Okay. And the same thing here. So, so I'm just going to put these in brackets in this way. I'm going to match up, or I'm going to combine the integral of u1 of x with I times the integral of v1 of x. And do the same thing with u2, integral u2 plus I integral v2. But again, I'm using this star here. I'm using the fact that that I know or it's on page 87, that the integral of real valued functions, the sum of real valued functions is the sum of these integrals. So this whole thing is integral u1 plus integral u2 plus I integral v1 plus I integral v2, and we're just putting them in brackets in such a way that by definition this is the integral of f and this is the integral of g. Right? And you can prove 3 in a very, very similar way. You first prove it for real valued functions. Again, it's very easy to do that because we know it's true for f plus and f minus, and the integral of f is integral f plus minus integral of f minus. So we do it for real valued functions, and then we do it for complex valued functions in the very exact same way. All right, and 2 is, as usual, this is true if and only if this here is not negative. Just bring this integral f of x over to the right-hand side. Okay. And from 1, we can write this as the sum of this difference here. And this is assumed to be non-negative. So whenever you integrate a non-negative function, you get something non-negative. Okay, so let's prove a very innocent-looking proposition. But the proof is very clever. It is probably the most clever proof, actually, we will deal with in the entire course. It's a very easy proof, nonetheless, and it's very elementary. Theoretically, you could prove this in Calc 1 if you want to, but it still is very clever. I honestly forget how to prove this, and I always have to remind myself what the trick is. And trust me, if you tried to prove this yourself, you probably will not do it. It's that tricky, but that's okay. Let's see what the trick is. And it's a very useful thing to prove. We'll use this a lot throughout the rest of the course. So if I have an integrable complex valued function, then the absolute value of the integral is less than or equal to the integral of the absolute value. All right, so this is where we need the polar form of complex numbers and these other facts that we reviewed. So in particular, the f is integrable, so the integral makes sense. It's a complex number. So we can write it in its polar form. Let's write it as r alpha, where r is, So let's say, actually, this here is z. So let's say this whole thing here is z. All right. So let's write this integral as r times alpha, where r is the absolute value of this whole thing, and alpha has modulus absolute value 1. It's a little hard to see, but right. Okay. So let's look at this. And it's an odd thing to look at, but let's look at alpha minus 1 times f of x. Okay, so alpha has modulus 1. So alpha, 1 over alpha makes sense. We defined alpha inverse, same thing as 1 over alpha in the last video. So let's call this, whatever this is, it's a complex valued function. Let's say it's u of x plus I v of x, where u and v are real. Okay, so u is real. Any real number is less than or equal to its absolute value. Again, this absolute value is less than or equal to u squared plus v squared square root. And that's equal to the absolute value of alpha minus 1 times f of x. But this, remember, is 1 because alpha has modulus 1. So u of x is less than or equal to the integral of f of x. And that's how we're going to relate this absolute value of the integral with the integral of the absolute value. It's through this chain of inequalities here. Okay. So absolute value of this integral is the same thing as absolute value of z. So actually, this is a bit silly. You don't really need z here. So let's just get rid of this here. And actually, let's say r is going to be absolute value of the integral of f of x dx. All right. So we're still putting this in polar form. R is just this absolute value, the absolute value of this here. Okay, and alpha is a modulus 1. Okay, so again, absolute value of f of x is r. R equals alpha inverse the integral of f of x dx. Why is that true? Well, it's trivial. Just multiply both sides by alpha inverse. That gets rid of this alpha here. So r is alpha inverse integral of f of x. Now I can pop in this complex number inside the integral, but that is u plus iv. Because alpha inverse f of x, we call u plus iv. Okay. Now let's make an observation here that's crucial. What is this integral here? You should be able to answer that question precisely. It's got to be 0. Why? Because this is a real number. The only way to have a real number equals a real number plus a complex, an imaginary number, is if that imaginary number is 0. Otherwise, it's not real. This is not even just real, it's non-negative. So this has to be 0. Okay? So this equals the integral of u of x. And finally, from what we've had here, that's less than or equal to the integral of f of x dx, because u of x is always less than or equal to the absolute value of f of x. So we really have to be pretty damn clever to relate this absolute value of the integral to the integral of the absolute value. But like I said, you look at this and every step of the way should be crystal clear. It's just what should be clear is the intuition on how to, I mean, maybe it is clear, but to me it's a little fuzzy sometimes thinking, oh, how do I prove this? What's the trick?